Welcome back, everybody. And in this second short video, I'm going to talk about how to make the maximum depth of a binary tree problem a bit better. So you can click the link that just popped up at the top corner of this video to check out the last problem, where I made the invert binary tree code a bit better. And in this episode, I'm going to make the maximum depth of a binary tree code a bit better. So I'll throw up another link to a video in the top corner. This is the video where I write the code that you see here for how to find the maximum depth of a binary tree, where basically you want to, given the root node, figure out how deep the tree is at the deepest point, where each node counts is one level. So in this case, it's 1, 2, 3 is the maximum depth. So the code I wrote to do this is here, and it works. I'll just run it on the test cases to show that. But this code is a little bit messy, and it's overly complicated. I wanted to see if there was a better way that this could be done, and there is. In fact, there's actually a way to do it in 4 lines of code, which I didn't actually believe when I was first looking through the solutions. But then I found something that struck me as nice and pretty intuitive. So I'm going to explain that here. So what I'm going to do is I'm going to leave this code down here and comment it out, just so we can see what I had done. So what we can actually do is, and if you watched my last video, I showed that there is a better way to start off one of these recursive tree functions in the case that the node is none. So we can say if not root, we can return 0 here. And that makes sense, right? In the case where we start this function and we give it something that is none, so it doesn't exist, the depth of that tree is 0. So that's all we're accounting for here. This also holds for when we're recursing down the tree. If we ever get to a point where we're down here, the children of the 7 node, and those are both none, we don't want to return any additional +1s for the depth, because it doesn't exist at any further level. So it makes sense that if we ever see this node being none, we should return 0. So that's 2 of the lines. And there's only 2 more to go. So in the case where this node does exist, what we basically want to do is, and I talked about this the first time I solved this problem, we basically want to count how deep the tree is on the left. So in this case, for the 3 node, we want to count how deep it is on the left. Then we want to count how deep it is on the right. And then we want to take the maximum of those 2 values. And that's exactly what I do here. I go over the left, adding 1 for each level. I go over the right, I do the same thing, and then I take the max of the 2. You can actually do this in a much simpler way by saying return max, just like we do down here. And instead of putting left total and right total, I can just put in this, the max depth of the left, and then the same thing, but with the right. And what this will do is exactly what we did down here, basically. It'll call this function recursively on the left subtree and count how deep it is. It'll call it on the right subtree and count how deep that is and take the maximum of the 2 of them. We just need one extra thing. You remember how I added +1 to each recursive call? So every time we go deeper in the tree, we're adding 1 so that we can keep track of how deep we've gone. We need to remember to add 1. And that formatting looks slightly funky. Let me make this bigger. There we go. We need to just add 1 to it. So what we're doing here is every time that we're at a node and it's not none, we want to check how deep the left and the right are. So we do that by checking the left here and the right here, taking the max of the two. And then we have to add one, because every level we go down, every recursive call we make, we want to make sure we're adding one to our depth, all the way until we get down to a node that doesn't exist, in which case we add 0. So what this looks like in this actual tree is, for the 3, we add 1. For the 20, we add 1. For the 7, we add 1, so we're at 3. And then we're down at a none value, which are the node 7's children. And for that one, we return 0. So it's 1 plus 1 plus 1 plus 0, which is 3. So yeah, that's how this one works. And then we can simply return max depth helper. We pass in the root. This is just to run the actual program. And let's make sure this works. And yeah, sure enough, this solution, while certainly not the fastest we could possibly do it, which isn't what I'm focused on in these videos. I'm focused on just explaining it and understanding it. And I think this is a really nice solution that's a lot simpler than my previous one. And this is also important because in the next video, I'm going to redo the diameter of a binary search tree, which required us reusing this code. So it actually makes the next video's code a lot simpler as well. So thanks so much for watching, and I will see you next time.